Right, so this is me. Yes, I've been writing Erlang for 10 years. I also wrote GenSMTP in addition to Logger. I did escape the data gravity. And I've been working at Helium about 4 years, fighting in the IoT wars. And additionally, I'm a bit of a blockchain skeptic. I don't hold any cryptocurrencies. I'm pretty skeptical of a lot of usage of this technology, but I would like to explain to you how it actually works and where it actually may have some valid applications. So I'm not going to talk about investment advice. I'm not a blockchain expert. This field is so new. There are very few, if any, experts, so don't trust anything anybody tells you. Do your own research. I'm not pitching you on an ICO, and because I only have 25 minutes, this is going to be not an in-depth guide.
Do you at least have a white paper for us?
Not yet. I have some other stuff I will show you, though, or give to you that you can look at after. So what is a blockchain? A blockchain is a way for a whole bunch of people, a whole bunch of things that don't trust each other at all and don't even know who each other are. As long as they agree to some very simple ground rules, they can actually forge consensus and make progress together. And even if some of them are acting maliciously or just broken or doing crazy things, you can rule them out. You can put them to the side and say, you don't get to play anymore, you're breaking the rules. Blockchains are usually decentralized. I would argue that centralized blockchains are kind of not really very interesting or useful. They're just really, really bad databases. And I know about bad databases. And then the real value in this is if you're decentralized, nobody gets to change the rules unilaterally. There's no company that's sitting there that says, I don't like you, you can't do this anymore, or I'm going to take your money because I feel like it, or I got acquired by some other company and now we're going to completely change the rules because business reasons. And if the protocol does need to change or the rules do need to change, it requires effectively a majority vote for that to actually happen. So a blockchain has about 4 pieces. The most important and sort of biggest area of diversity is in the consensus algorithm. And of course, the consensus algorithm is useless unless you have a way for all of these things to talk to each other. And because they're untrusted, you don't really know who they are, you have to have kind of a peer-to-peer style network. You can't use distributed Erlang for this because distributed Erlang implies some level of trust. So you have to have a very kind of flexible networking layer to actually get the things to talk to each other. Then you define what kind of transactions are valid against the state of your blockchain, and then you define how you bundle those transactions up into a block and how those blocks are validated, are they created, how those kind of things. So consensus is how everybody agrees on something is happening. And usually it really revolves around, are the transactions valid in this context? And can we all compute the same value for some aspect of the system? And consensus, as I said, is a very wide field. There are lots and lots of different kinds. Some are good, some are bad, some are proven correct, some are not proven correct, and some have been broken. So this is probably the biggest area of research in blockchains right now, is finding good consensus algorithms that suit very specific use cases. And sort of, you have trade-offs. Some are fast, some are slow, some use a lot of power, like Bitcoin. Some tolerate a very low percentage of malicious actors, or none. Again, not very good. Or they have a lot, and then they can have a slider depending on how easy it is to participate in the blockchain. Are you in the inner circle of the blockchain, or are you kind of on the outside looking in? So on the peer-to-peer network, obviously communication is the fundamental thing you need to build a distributed system. And you have to communicate in a diverse way. If you're only talking to a very small set of peers, they can feed you bad information, and they can actually trick you into either violating consensus, or they just hide information from you that you need to make this decision that everybody else on the network is seeing. So you have to be very careful that you can't sort of be on a dead-end street on the internet. And the modern internet is really kind of difficult to do this on. We've got NATs, we've got firewalls, we've got lots of IPv6 that doesn't actually work, thanks Comcast. And a lot of blockchains have a whole peer-to-peer library built into them. A lot of times it's not easily abstracted, which is annoying. I think we're getting to that point, and we'll talk a little bit more of that in a minute. And then you don't actually usually encrypt blockchain traffic. You authenticate it, so you know that you're talking to who you think you're talking to, but just anonymously. You just have an identity you're talking to. It doesn't matter who they actually are, just that they're a countable entity. And you basically just authenticate with signatures and stuff like that. We don't actually do you don't need to do a lot of encryption because the blockchain itself is public. There's no real point in sending private information on the blockchain, sending private information between peers if the result is going to be public anyway. And transactions effectively can think of like queries against the database. You're gonna submit some operation, something's going to change, and you'll get back a result. And depending on the blockchain and implementation, it could be, moving coins around. It could be passing an argument to a smart contract. It could be, fetching a piece of data out of a smart contract. Whatever. You get to choose what those mean and how they're implemented. And as I said, blocks are kind of like checkpoints in a database. There are a whole bunch of transactions all rolled up. They have a total ordering, which means that one block follows the next. You can't skip blocks. You can't reorder blocks. They're only meaningful when you have them in their intended order. And additionally, because the blocks are linked, you cannot alter a block in the blockchain without invalidating all subsequent blocks, which means they're tamper-proof to a degree. And there's really three major kinds of consensus you'll see in blockchains today. We'll see the practical Byzantine fault tolerance was kind of that was the original kind of distributed consensus, untrusted consensus model. And we see a couple cryptocurrencies that use that, like Ripple and Stellar are probably the most obvious ones. Then we have Nakamoto Consensus, which is what you probably think of when you think of a cryptocurrency. You think of, oh hell, my laptop's really hot, what is it doing? And that's because Nakamoto Consensus is effectively tied to just burning your CPU as fast as it can. And Bitcoin and Ethereum currently are using it. Most cryptocurrencies use Nakamoto Consensus. We have a new challenger in proof of stake. So Ethereum is the big one trying to move to that because there are obviously the problems with Nakamoto Consensus around power consumption and just being kind of terrible in general. And then there's a whole bunch of kind of weird, they don't really fit into a good bucket. Filecoin's a good example. They're working on an idea of turning empty disk space into a consensus model. So what is practical Byzantine fault tolerance? As I said, there's lots of variations. The original paper was in 1999, and there's been an explosion of alternate implementations and riffs on that original design. Originally, the membership of the replica set in PBFT was closed. You had to be kind of blessed by somebody to get into that set. So effectively, replica sets were trusted in some way. There are now versions of BFT that have open membership, but once you have open membership, and if anybody can join the consensus, I can have a computer that pretends to be 5,000 people. They all join the replica set, and now I have the majority, and I can do whatever I want. I can take the train off the tracks, no problem. So a lot of times you'll have some kind of requirement around membership where you either have to have some other asset to say, I have enough tokens, so I'm trusted and I can be in the replica set. And if you have a closed replica set, it's not really a blockchain because you're restricting access, which means there's still some gatekeeper there. If the gatekeeping is tied to a central entity, you become centralized again and you're back to being a terrible database. So the way PBFT works very briefly is the client sends its transaction to a primary, the primary sends it to all of the replicas, and then all of the replicas reply with their results back to the original client. And the client knows when he knows how big the replica set is, so when he sees 2/3 majority of the replica sets agree with him, he knows that we've reached consensus. Very simply. Nakamoto Consensus has open membership because they defeat Sybil attacks by effectively requiring you to have a massive amount of compute power. Because you can't in parallel compute two things on the same CPU at the same time without lowering the computational speed that you're doing both things at, that's effectively a fundamental scarcity that is not. If you have this much hash rate, you can't also have that much hash rate under a different identity. So it prevents the idea of just creating a whole bunch of fake identities that can defeat consensus by majority rule.
Unless you have a lot of money.
Yes, but okay, so and effectively it works in Bitcoin by you have a block, you have a magic field, and you run SHA-256 over this block until by tweaking the magic field, the integer value of the hash is under some work limit, which adjusts depending how much computation is in the network, and so it goes up over time, and it just gets more and more expensive. And it's actually really easy to implement. And I would like to show you, but I can't. There's no time. But we'll talk about that in a minute. But it is very easy. But obviously, it's terrible for the environment. It's terrible for people trying to buy graphics cards. It's terrible for pretty much everything else, other than it's easy. Proof of stake is where I have something valuable. I have some valuable asset that, you say if you're rich enough, you can be in the replicas. You can vote on the consensus, and if you vote badly, we get to take your money away. And as I said, it's a lot of people are looking at this right now because of the problems with Nakamoto Consensus, but we haven't really seen a big deployment of a proof of stake blockchain. People are still trying to work out some of the kinks. So how does this all kind of relate back to Erlang, and why would you even write a blockchain in Erlang? So, most blockchains in Erlang, or most blockchains are written in C++. A few of them are written in Go for some unfathomable reason. There's a few things in Rust, but now actually I looked and there's at least 4 different blockchains in Erlang at the moment. So Eternity, who somebody else is giving a talk on that. Arweave, they're also here. There's somebody doing something called Urcoin, who I don't know if they're here, and I'm working on one. So you're pretty lucky, because if you want to talk about cryptocurrencies, there's at least 3 teams involved in this field at this conference. So kind of a surprise to me when I filed my talk and saw all the other talks that were approved. I was like, wow, this is cryptocurrency heavy. Erlang has some great tools for actually building robust, reliable, distributed systems. So, we got QuickCheck, we got Dialyzer, we got Common Test, so why not? And one of the other nice things is that because there's 4 other teams, or 3 other teams, there's a whole bunch of open source code getting developed that make building these things easier and easier. And these are some of the things we've put together. So we have libp2p is designed by the people behind Filecoin, Protocol Labs, also the people behind IPFS. They've been trying to design. They've kind of designed a peer-to-peer network. We're not really compatible right now because I actually don't like some of their designs. So we're semi-compatible with libp2p. We may try to unify that later. We have some supporting pieces for libp2p, the multi stuff. I don't really have time to talk about what that is. We have a way to. I wrote a library recently. It's very small, but it effectively does public key compression for certain types of elliptic curve keys without being patented, which is kind of nice. It halves the size of your public keys, which is good for when you don't have a lot of room on the radio packet. We have a KD tree, which is a nice geospatial data structure to work with. We have yet another Merkle tree, but this one is a little bit more geared towards blockchain uses than the other ones that are out there. And I also wrote, which I was hoping to show at this talk a little bit more, but I actually wrote a cryptocurrency as a demo for this talk. So github.com/helium/beamcoin if you want to see a distributed blockchain in less than 500 lines of Erlang. There's your link right there.
You have an ICO?
No. But if you want to come and, we can, if you want to mine it with me at the conference, we can probably set up a little network and mine it, on the Wi-Fi here. So we're going to do something a little bit different now. We're going to talk about something now we've covered what a blockchain is, how the heck do you what is it actually used for? What are we going to use it for? What are we thinking we can actually use it for? So we have to talk about the IoT. And I'm kind of sick of talking about the IoT because it's been so long and we still don't really have a practical IoT. Like, we've got lots of bits and pieces, but nobody's really, I don't know, it's just, why, so there's problems with this, right? So if you go look at the IoT, you're like, I want to buy an IoT, and there's like, okay, you've got 20 different kinds of IoT. Some of them are a whole suite of things. Some of them are one piece, and you're like, okay, well, I'm welding these three things together, and it doesn't work. And so there's a huge amount of failure in IoT deployments because all of the pieces don't fit well together. A lot of times there's these vendors that are basically using the notion of an IoT as a way to kind of get you locked into their platform. There's going to be a patent, or there's going to be a license, or there's going to be something hiding that when you get to a certain point, then you step on the trap and you're caught. So a lot of companies are very hesitant. It's difficult to own your own data a lot of the time. A lot of times the IoT platforms you use will be like, well, we get to see your data as it traverses our cloud, which is not great for a lot of people. And at other times, when maybe you build an IoT infrastructure and your neighbor has built an IoT infrastructure, and those things are not interoperable either because they're different protocols, different things, or even worse, they are the same thing, but because the trust model in that IoT design doesn't allow multiple users of the same infrastructure, you're effectively not able to share those gateways and that kind of infrastructure. And obviously, you have the concern about what happens if the entity behind the design, the thing goes out of business. Is all of your stuff just expensive bricks at that point? So we've been in this for a while, and we're sick of it. We're part of the problem, to be honest with you. But we're seeing this lack of traction. So what we're going to do is we're going to blow the whole thing up and build something from scratch. No patents, no licenses, none of this nonsense. Everything is open source, and it's going to be properly decentralized so that anybody can put a gateway up, and then anybody else can use that gateway. And it's kind of like public Wi-Fi, exactly. It's much more like the real internet model that we're used to. It's not one of these kind of like a toll bridge kind of thing where you got to pay to get on to sort of you got to pay the constructor of the bridge. So one of the things to do this is how do we allow all of these gateways, and without any centralization, how do you build something like this that can actually work? And one of the big things that you need is some kind of, just like in Bitcoin where you use CPU power as a proxy for identity, you can actually use radio bandwidth and location to construct an identity that is resilient against Sybil attacks. And sort of the real premise here is that instead of using something very expensive and pointless like Bitcoin mining, you can do something around radio packets and location that actually give you an equivalent proof of work, but it's actually useful proof of work because you're also verifying the integrity of the network at the same time. So it's like Bitcoin, except if Bitcoin was also folding proteins and actually doing something useful instead of just calculating SHA-256 over and over again. So how does it actually work? So basically what we want to do is we want to verify a gateway is where it says it is. We want to verify the gateway is actually listening for radio packets and not just pretending to be there or claiming that it's there. We want to verify that the thing actually has a radio to transmit again. And as I said, that lets us build these resistant identities, Sybil attack resistant identities. So how does it actually work? So the first step is a gateway is trying to mine a new block. And he looks at the blockchain, and the blockchain has something it does, and it spits out a target. It says, you're in charge, this block, of verifying this other guy. So basically what he does then is he goes out and he figures out, because all of the gateway locations are published to the blockchain. So the challenger knows the topology of the gateways near the target. And he says, okay, who's nearby that I can use to verify this target that I have? So he constructs a map of regional gateways. Then he figures out a path that intersects that target, and he constructs an onion packet like how Tor routing works, where you encrypt each layer of the onion packet with a key unique to one of the actors in the system. And then you send that around the network. Each layer is decrypting it, they're sending a receipt, and it's going on to the next level. And because nobody knows, because it's all broadcast, nobody knows who the next hop is. They just have to broadcast, and radio waves just take care of the thing. So once the challenge packet gets somewhere, either it makes it all the way to the end or it dies along the way, kind of like traceroute, you now have some proof of what that network in that region is like. And you also have a way to anchor that proof in time. So you can say, at this point in time, in this space, we at least know there was this much network coverage. And you actually, instead of in Bitcoin where the first block wins, you actually have multiple gateways all competing to provide this proof attached to their block. And then we pick the best proof of coverage. We pick the best block, which has a large factor of being a good proof of coverage, which means that we then encode that knowledge we had about the network at that point in time into the blockchain. And then everybody who thinks that that is the best block, they all start mining on top of that block. And that's how they vote for consensus. So all of this screwing around, what was the point of all of this? So one of the really good things is that we can actually verify the integrity of the network and encourage people to maintain their network coverage. There's actually an incentive here. Either you'll get paid for verifying coverage, and if you don't have enough trust score, you haven't been verified recently enough, you won't be able to mine. So your incentive is to actually keep your gateway online and actually not have a fake gateway that doesn't actually provide the services it claims to provide. It also gives us redundant wireless coverage because for this thing to work, you actually have to have gateways see each other. It gives us a cryptographic proof of space and time. One of the things I skipped over is that our gateway actually uses a software-defined radio, which means that unlike a regular radio that gives us a very loose timestamp of when it saw a packet, we can, within 5 nanoseconds, pretty much say when we saw the packet. And if you have enough copies of the packet from enough gateways, you can do a time delay of arrival solution and solve for location of a transmitter without any special hardware on the transmitter. And finally, the network can actually kind of make money from its own existence, right? If you pay for packet routing, you pay for mining, the network is kind of getting rewarded for verifying itself and providing transport. So obviously there are other things out there, but we kind of don't really think that any of them kind of provide all of these kind of pieces all together. There's always going to be a patent, there's always going to be a license, there's always going to be a SIM card, there's always going to be a central authority saying, I don't like you, you don't get to play in my sandbox. Or the price is going to be really high. And that's probably what's going to happen with a lot of these cellular IoT approaches. The carriers are just going to be carriers. They're going to charge you a lot of money. We're already seeing that happening. And then another nice thing about this is you can actually mix corporate deployments and personal deployments to make a single seamless network. Obviously we have cryptographic proof of location, so that's something that we think could really enable a whole bunch of more use cases. If you can prove that this device, which has its own cryptographic key burned into the hardware, was at this point, at this time, we think there's a lot of use cases out there. You can't do that today. There is no real way to do anything in that kind of realm. And again, we have built-in support for geolocation. Now, unfortunately, I don't have anything else to show you. No white paper, no real code yet. We've got all the bits prototyped, and so we're 90% done. We have 90% left to go. And this was not supposed to be the initial announcement of this, but because timelines are timelines, this is the first time anybody's heard about this. So you were in the room when we announced this. But more stuff is going to be coming out soon. We're gearing up the marketing machine. I don't think we have time for questions. I'm only 3 minutes over, but anyway, I think that's the end. Thank you.
Just one real quick question. If everything is free, so revenue?
So think of it, okay, so you build a network and you are invested in the success of that network. It's more like, if we don't succeed, if the network doesn't succeed, we don't succeed. But we do not extract revenue directly. We are sort of more like the Red Hat model where we're providing pieces, we're providing design support, we're providing, potentially maybe some peripheral services that are useful, like potentially a location software, peripheral pieces that add value, but the fundamentals of the network are completely open. Hardware, software, No licenses, no weird patents, nothing like that. So